Hello everyone, welcome to the Logical Loop channel. Today we will discuss another lead code problem of the day. The problem number is 648, redundant connection. Okay, so in this, let's see the statement. In this problem, a tree is undirected graph that is connected, has no cycle. Okay, a tree is an undirected graph and that is connected and has no cycle. You are given a graph that is started as a tree with n nodes labeled from 1 to n with one additional edge added. Okay, one additional edge is added. The added edge has two different vertices chosen from 1 to n. Okay, and was not an edge that already exists. Okay, the graph is represented as an array edge. Okay, we have the edge graph. In that we have AI and BI indicate that there is an edge between the nodes AI and a BI in a graph. Okay, return an edge that can be removed so that the resulting graph is a tree of n node. There, if there are a multiple answers, return the answer that occurs the last. Okay, so suppose we have we have the graph we have the graph like 1, 2, and 3, and in this we have the connecting is like 1, 2, and after that 1, 3, and then we have the 2, 3. Okay, so in this we have to remove that edge in that is causing the redundant and that is causing the that cycle. Okay, we need to remove that. Okay, so let's see, we can remove this 1, 2. Still 1, 3, and 2 is connected. Suppose we have removed this 1, 1 to 3 edge. Still 1 and 2 and 3 is connected. But in this question, the thing is mentioned that we need to remove the last one. Okay, so that's why we will remove the 2 and 3. Okay, so in this, what can we do? Like the brute force we can we think of, we can apply the BFS or a DFS. Okay, on every edge we will traverse, and for this U node and this V node we will apply the BFS and DFS if we are if that is in the adjacent graph, and if we are able to move from 1 to 3, then we will return that particular edge that this edge is already exist and we need to remove this thing. Okay, let me show into to the code. First, I will applying the BFS. BFS, you can apply DFS or anything. Okay. Uh, in this, I I am applying BFS traverse on every edge and find out the in adjacent graph. Okay, so first of all we will take length, and which we have like this, and we will take adjacent for creating our graph. For let okay, uh let you. Okay, now here we will check if adjacent has u and adjacent has v and BFS has adjacent u, and we have the visited array, because we need to track visited also now, because we need to see if we are able to move from u to v. Okay, if we have, we will return that current edge. Okay, otherwise we will push. If first of all we check if edge don't have u, adjacent set u with this, and adjacent get u push v, so we will have uh, like this. And if don't have, we will set v with. Okay, we are simply we are making the graph. Okay, and here we will push u, so this edge will be formed because it is an undirected graph. Okay, and after that we will return empty array because we don't find anything in this. Okay, now we will need to write the BFS. Okay, sorry, BFS, adjacent U V and visited array. Okay, first of all we will mark visited of U equal to true. We will take a Q because in BFS we need a Q. In Q we will push the initial one, this U. After that we will take a pointer to take it from the Q from the front, and while front is less than Q dot length, simply we are applying the BFS. We will take the current node Q from front plus plus, and if this current equal to V means if the source is equal to destination, which means we have reached the destination, we will return true. Otherwise we will move to the next node of adjacent graph, which we have current. Okay, and if we see if this is not visited, next node, what we will do, we will push the next node into the queue, and we will mark this equal to true. Okay, and after that we will return false. Okay, let's see, let's run it. Okay, so these example test case is passing, and in this the time complexity will be we are like traversing over the length, and in this we are applying the BFS for every edge the BFS will happen. So the time complexity will be n to the power square, and the space complexity we are simply taking the map, so the n. Okay, let's submit. Yeah, so all the test cases passing. And let's talk about the optimal method in this. Okay, so what we are doing, simply we are breaking the redundant edge in this particular graph. Okay, so in this what can we see, basically if we, because we are not adding any extra edges, we are not adding extra noded into this graph, simply we are seeing this like this graph is a one component or not. Okay, one component and or not. So when the case of one component, we can think of the DSU, disjoint set units. Okay, so yeah, we will apply the DSU in this. Okay, see, like one and two, like one is a parent of two, like that. Okay, and then one and three, like one is also a parent of three. So in this, like we are able to move from like a three to two. Okay, so that's why there no need to of two and three edges. So that's why we will remove it. So let me show you this use of DSU. Okay, for DSU we have to make a DSU class, and in this we need to take a constructor. We will take let, okay, sorry, we will take this parent equal to array of n plus 1 with 0, and we will take this dot rank array of n plus 1, which we will fill with 0. Now we will fill the parent, this dot parent of I. Okay, like for initially, like for every node, this is that is their own parent. Okay, now we will use the find. Like if x is not equal to this dot parent of x, what we will do, this dot parent x equal to this dot find, we will pass the parent x. Okay, after that we will return this dot parent. Okay, Now we will use union of x and y. Okay, let x parent will be this dot find x. Let y parent equal to this dot find y. And suppose if x parent equal to y parent, which means they are the both same parent, we will return it. Otherwise, we will see if this dot rank of x parent is smaller than this dot uh, rank of y parent. So this dot parent of x parent we will make y parent, simple. Else if this dot rank of x parent is greater than this dot rank of y parent, what we will do? We will simply make this dot parent of y parent equal to x parent. Otherwise, we will do this dot parent of y parent equal to x parent, and we will increase the rank of x parent by 1. Okay, now we will use this DSU. We have the DSU, and this for we will have the let u equal to edges of I and 0. We will have v edges of 1. Okay, and if DSU find u, means if they have the same parent, which means we need to return the current edge. Okay, otherwise we will join them, we will union them. Okay, u and v. If we don't able to find, return empty. Okay, let's run it. Okay, so all this example test case is passing, and in this the time complexity is simply we are like iterating over till a length of the edges, and in this we are using the edge and we are using the find union. So for the time complexity of the DSU of the union is like alpha n, and alpha n is the like length of the array, length of the rank and the parent array. So the overall time complexity will be, we have the n alpha of n. This alpha of n is the length of a parent or a rank array, and the space complexity is we are taking a DSU, so that space complexity will be n. Okay, we will submit it. Okay, so all the test cases passing, and I hope you guys understand it. Thanks everyone.